All right. So the lecture today is going to be basically encompass three different experiments, if you would, right? It's all going to be torsional deflection. But the first part of the experiment is going to look at torsional deflection of a solid rod. And we're going to look at deflection of a brass rod and a steel rod. And the second part is going to look at the effect of rod length on torsional deflection. So we're going to change the length of the rod and see how a particular torsion or torque is applied going to affect the different lengths of that same rod. And lastly, we're going to try to compare torsional deflection of a solid rod compared to a tube or a hollow rod, if you would. Right, so there's the three things we're going to try to cover today. The report for this lab, the Torsion lab, is going to be doing 2 weeks, 1st, 2nd of April for you guys. Right, next week we're going to have lab, but basically I'm just going to open it up next week and take any questions you might have. If you all want me to maybe even work an example, draw some graphs or anything to that extent. I'm considering maybe posting, maybe for experiment 1, because I already have that. I could possibly post my Excel sheet for that, maybe. I'm considering that, but we'll see how that goes. But I think I'm going to kind of wait till next week and see the types of questions I'm getting from you guys. All right, so next week is just going to be an open session, and we're just going to kind of talk through how, or what I expect in the report, or how you want to write the report, or maybe even how to analyze the data that you do have. All right, so these are very good equations or relationships to know. And if you were in class with me, I know not everybody in my class, but if you were in the class, we already went over these concepts. But for those that were not in class, even if you were, basically phi is the angle of twist, right? That torsional deflection.
Professor Macaulay.
Yeah.
Are you hoping to be sharing your screen with us? Because I don't see your screen.
Well, thanks for saying that. I am supposed to be sharing my screen. Share. All right. The phi, which is the angle of twist or that angular deflection, phi is equal to TL over GJ. I always try to remember it as TL over JG. So phi is equal to TL over JG, where T is the torque, L is the length of shaft, right? So that's this length here. What is G?
It's the modulus.
It is a modulus of what?
Rigidity?
Yes. So G is the modulus of rigidity, or you can call it the shear modulus. And what about J?
Angular polar, or polar moment of inertia?
Exactly. So J is the polar moment of inertia. Awesome. If you're looking at torsional stress or torsion stress, that's tau. You can use this relationship for torque times the radius, right? That's the radius of the diameter, that cross-sectional area. So torsion, or the torque times the radius divided by that polar moment of inertia. If you also want to look at strain, torsional strain, so let me go back to, well, torsional strain is given by this parameter here, gamma, right? So if I go back to this diagram here, you see this shaft is fixed at this end, and a torque was applied to this end, right? And therefore A, at that point A, was displaced to point B, and you have theta on the cross-sectional area, right? So the angle that the cross-sectional area moved is phi, not theta. That should be theta. I mean, it's phi, should be phi, right? So that's the phi angle, that's the angle of twist. But if I look at the movement or the deflection of the shaft, if I go from A to B, this shaft twisted right? From A to B, the length of the shaft, and it created an angle of twist as well along the shaft. But we call that gamma, and gamma is, in fact, our strain, right? So we look at the angle formed along the shaft as the strain, and the angle formed on the cross-sectional area as the angle of twist, that phi angle, angle of deflection, right? So two different things, but we can relate them here as that torsional strain is equal to the radius multiplied by that phi angle divided by this z length, which is actually the length of the shaft, right? So torsional strain equal to the radius multiplied by the angle of twist divided by the length of the shaft. All right, so that's your relationship for torsional strain as well. Hooke's law, we know Hooke's law as when we look at normal stress and normal strain, right? If we relate normal stress to normal strain according to Hooke's law, we have the modulus of elasticity as that proportionality constant, right? Stress is equal to the elastic modulus E times the strain. We can also look at Hooke's law for shear stress to shear strain, right? So the proportionality constant would be G, which is the shear modulus or modulus of rigidity, right? So therefore, shear stress is equal to shear strain, I'm sorry, is equal to shear stress over G, right? Or maybe the easy way for you to remember it would be shear stress is equal to G times the shear strain, right? Similar to normal strain, normal stress equals to E times the normal strain, right? So we have a relationship for strain, shear strain as well, based on Hooke's law. You have another relationship for strain, right, based on the angle of twist. But what about the two modulus? We've talked about elastic modulus E and modulus of rigidity, G. Right? You can also relate those two with this equation, and this equation is based on elastic theory, right? So if you were in the plastic region, this equation does not apply, right? So based on elastic theory, we can relate G and E with this relationship here where this term, this parameter is a Poisson's ratio. And again, if you all remember
If we're in which region?
Elastic region. So basically, if you look at a stress strain curve, that linear portion, that initial linear portion, right? If you go past that, if you go past that portion, basically, if you put a torque on this shaft, and that shaft cannot return after you take that torque off, cannot return back to its original position, then you have exceeded the elastic limit of that shaft, of that material, right? You want to make sure that you're still in the elastic region. So you can have a twist, but if you take that torque off, it should go back to its original position,
Okay.
right? And because you were in that limit, you haven't exceeded or entered into the plastic limit or plastic region, then this equation can apply. You can relate the two modulus using this equation with Poisson's ratio. Right? Poisson's ratio, again, is just lateral strain over longitudinal strain. All right. So I took this from the FE exam, right? This is directly off the FE exam. And one thing I know it's probably going to take some of you maybe 2 years before you all do the exam, but I do have juniors and seniors in the course as well in the lab. So, so I pulled, I think I got 3 questions that I'm going to run by you guys and try for you all to try to calculate it. So based on what we've just talked about, I want you all to look at this and see if you all can determine what the shear strain is. Now, pay attention to your units, okay? I'm gonna give you all about a minute and see if y'all can come up with the equation, with the answer. All right, does anyone have an answer for me yet?
I got 1.67 times 10 to the minus fourth pascals.
Okay, so I believe that's in the ballpark. I can't remember the exact number. I'll show it to you here in a minute, but it has to be small, right? We're talking about strength value. So we know it has to be small. So you had 1.6 times 10 to the minus 4. So you're probably going to be correct.
I basically rounded that to 0.002 newtons per meter squared.
So we calculate shear strain, right? So you should not have,
Oh yeah, that's right. No units.
right? All right. So the answer is, in fact, 1.67 or in times 10 to the minus 4. Therefore, your roundup number would be correct. I would suggest that you try not to round up, or if you're going to use, well, yeah, so try to use 3 significant digits in your numbers at the very least, right? So
Okay.
yeah, so that would always be good. But this question really, as far as the FE exam goes, this is really just a test on if you pay attention to units, right? They give you 15,000 kilopascals and a modulus of 90 gigapascals, and they just want to make sure you're paying attention because they're probably going to give you an answer where they did not do anything with the units. Therefore, if you're not paying attention to the units, you're going to get it wrong. So be aware of your units, right? So gigapascals in terms of kilopascals will be times 10 to the 6, right? Giga is times 10 to the 9, which would be pascals, but then to get that to kilopascals, it'd be end up being times 10 to the 6. So 15,000 divided by 90 times 10 to the 6 should get you the strain. All right, so basically that's just Hooke's law, right? Relationship of shear stress to shear strain. All right. So we've talked about torque, right? That application of torque, you're gonna get that angle of twist based on how far this part of your cross section moves, and then your shear stress or shear strain based on how far the length of the shaft deformed, right? And we've also talked about this relationship. So on to the next page. This I get directly off of your textbook, right? You can go to the back of the textbook or you can go online and get these reference values. But you're going to need these for the analysis, right? So this is from the back of your textbook again. For steel, modulus of rigidity or shear modulus is 11.2 times 10 to the 6 psi. And for brass, it's 5.6 times 10 to the 6 psi. So as you can see, steel has twice as much as in magnitude as far as modulus of rigidity goes, right? 5.6 here to 11.2 for steel. All right, so here's another question for you guys, and I'm gonna try to give you all another minute or so to try to work through this one. Is asking for shear modulus or modulus of rigidity. It gives you E in Poisson's ratio. All right, so go. All right, does anybody have an answer?
$11.9.
11.9. All right, if you didn't work the problem or you're trying to figure out how to work the problem, you got a modulus of elasticity of E, right, which is 33.3 gigapascals. And you're given Poisson's ratio and you're asking for shear modulus. So in essence, elastic theory is what I would go to and look at this relationship. And you try to use that relationship to calculate the shear modulus. And of course, you should get 11.9 gigapascals. All right, so I hope everybody got that answer. So
Yes.
awesome. So J, we've talked about the torque. Let's talk a little bit about J. How do we calculate J? J is polar moment of inertia, and the way to calculate for a solid section, assuming this is all the same material, right? J is pi times the radius to the fourth power. A is the radius. So pi times the radius to the fourth power divided by 2. What if you have a hollow section like this shown here? All you need to do at that point is find J for the assuming you have a solid section, right? And then find J for this inner part, which is hollow, and subtract that from what you have for the outer part. So in essence, it'd be, since the diameter for the inner is B, right? It'd be pi A to the 4 divided by 2 minus pi B to the 4 divided by 2. And that relationship, if you reduce it down a little bit, you should get this relationship here. But I think it's easier just to think, if you want to do it for a hollow part, pipe, cylindrical pipe, if you would, just do it for, get J for the outer section, get J for the inner section, and subtract the 2. All right. So I think this might be the last question that I pulled from the FE exam. Let's see, it says an aluminum bar, 17 meters long, right? 0.6 meters in diameter. We have a torque applied that's 11 kilonewtons per meter, right? And it's asking you, no, it says the shear modulus of elasticity. That's not correct. That can be shear modulus of elasticity. Okay, I guess it is elastic because it's in the elastic region, but it's confusing. So that should just say shear modulus, right? So let me do that. Shear modulus G. Save. Right, the shear modulus is 26 gigapascals and is asking for the angle of twist of that aluminum bar, right? Angle of twist, again, that's that phi angle right here on the cross-sectional part of the shaft, right? So again, phi equals TL over JG, right? So give you all another minute, try to see if y'all can come up with the answer for me. All right, anyone get an answer for me yet?
I got 0.004 degrees.
0.004 degrees. All right, so you used the equation as is, right? TL over JG. And then you had 0.004, is that correct?
No, I got it in radians and then converted to degrees.
Awesome. Okay, that was the point I was trying to make, right? So for those of you that may not be familiar, that equation, phi equals TL over JG. Let me go back to it right here. Phi is equal to TL over JG. This equation gives you phi, the angle of twist, in radians, right? So if you use the parameters, the values for these parameters, making sure that they're in similar units. Let's go back here. We have meters, kilonewton meter. So therefore, maybe you want to put your shear modulus in kilopascals, which is kilonewton per meter squared. And all your units should be okay and everything would cancel. But you're going to have an answer that phi is equal to, I have 5.6528 times 10 to the minus 4. But it should be a small number because it's going to be in radians. So if you don't have a small number, then you need to go back and recheck that, right? So this is going to be in radians, right? And if you want to convert it to degrees, of course, it's 180 over pi. I think most of you probably think about converting degrees to radians as 180 over pi, or if you think full revolution, 360, that's 2 pi. Right? So you can convert radians to degrees using that relationship. And 0.03, I think, was that Patrick that said 0.04?
Yeah, I realized I used the wrong equation for J.
Okay. All right. So I hope y'all can understand the process. And again, these are FE exam questions. So these are questions that you're probably going to see later if you do take the FE exam or in the exam. I don't know. In my class. Torsional stiffness. Right? Torsional stiffness. If you think about it as just the torque divided by that angle of twist, in essence, think about it this way. Right? If you're looking at the stiffness of the material, is what torque is necessary to apply to affect just one unit angle of twist, right? How much torque do I have to put on the shaft for it to twist 1 radian or 1 degree, right? That's in essence what torsional stiffness is, and therefore you can calculate torsional stiffness (KT) as the torque divided by your angle of twist. All right. So my original plan was to actually have a live video of you all watching Nick do the test, but that was not possible. And then we tried maybe have the video pre-recorded, but then Nick had some issues that he couldn't do it, and he's going to end up doing it on Saturday. But of course, that was late for my class yesterday and for you guys as well. But the Dr. Lee's section can still use it. So he's still going to do it on Saturday. But we hope, excuse me, we hope we can get you a pre-recorded video of the Charpy test for next 2 weeks, in the next 2 weeks when we look at Charpy. But for now, I found this video online, and it's actually the same equipment that we have, and he's actually running the same test that we were supposed to run, right? You are not going to hear him, so I'm going to try to talk through as he does the test, what he's actually doing and saying. So, but you have the link, so make sure you find time after this to watch the video yourself, because I'm not sure if him doing the experiment and me trying to talk, is going to really give you a really good understanding of what's going on, but I'm going to try. All right, so here goes. All right, so there's 3 different circular sections, 3 rods that we're going to test. A solid rod that's steel, a solid rod that's brass, and then another brass tube. Right, so he's saying there's a rubber stopper on this end because it protects a sharp part. And you would also need to measure the rod using a tape measure, and a diameter using that caliper there. So he has the steel rod in his hands, and he's already measured it and put some marks for distances. As you can see, there's white marks. It's kind of hard to see. So he's got the sections marked where they're marked 500 millimeters, 400 millimeters, 300 millimeters. He said before you put the rod in the equipment, you need to adjust this to 0. So this is what you're going to be reading as your angle of twist. So you need to make sure that was 0 before you start. And then you insert the rod on this end. And into the chuck on this end. It said, remember to always have the rubber stopper on this end. That's a sharp edge, so you don't want maybe somebody to get hurt. So now you're going to input the rod into here, and then you're going to try to tighten the chuck down. But you're going to try to tighten it down and make sure you are at that mark that he marked right there. And what you got to think about is as you tighten that chuck, that grip is going to go out. So you need to adjust your rod to make sure you get the mark still at the end after that grip comes onto the rod. And then after you do that, then you take that key to tighten it down. And there's 4 bolts at this end, and you take them out, and that allows you to move this end so you can get the exact length that you need. And so he's loosened that end, and now he's going to move this till he gets his other mark at the end, at that end. So he's got exactly the length that he needs in the setup. Then he tightens everything back down. So now he's saying he's got exactly 50 centimeters or 500 millimeters of length. So he's pointing to the force gauge right here, and he said you need to make sure that's also 0. He's saying so where you zero it is right up here. And so you adjust that right here till you get 0 on the screen. So now you have 0, but there might still be a slack in the equipment, in the rod and the equipment. So you always want to make sure you put some small torque on your rod and then go back and 0 everything. So he's now tightening all these bolts. So he's still keeping his 500. And then he's going to now start applying a small torque to the rod just to make sure everything's engaged. And it's a small torque, and I think it's in your manual, the lab manual, but I think it's maybe 0.05. And after you put that torque on there, of course, this is going to change. So you got to go back and 0 this as well, right? So you 0 that again. So now you're at 0 before you actually start the test. And similarly, you need to re-0 the force as well. Right, so you start at 0. So if you're at 0, your angle of twist should be 0, right? That would be the first part of the data sheet that you might have filled out if you were doing the test. And now you start increasing the torque using that knob that he's turning now. And then you turn it up to 1 Newton. So you apply 1 Newton of force, and you do it very slowly till you get up to 1 Newton. And then you're going to read the angle of twist. And that angle is actually read in degrees, I believe. So now you need to do it 1 Newton at a time, all the way up to 5 Newtons. So you increase it again to 2 Newtons, and then you read the angle. You do it again, 3 Newtons, 4, 5 Newtons. And every time you read 3, 4, and 5 Newtons. And every time you read the angle of twist. And then you can do it again for the other rod. This was a steel rod. You can do it for the brass rod. But trying to take the rod back out you need to make sure you zero everything again. So after you zero everything, then you can undo the thing. Now, what he's doing is the second test, which is trying to change the length. So his initial test was for 500 millimeters. So now he's changing the length, right? And he's going to move it to the next mark that he made. And then he's going to tighten those bolts. Then he's going to come back and tighten the chuck on the right side. So he's got everything tightened for 400 millimeters now. But then you got to repeat the same process. You got to apply that small torque, right? And zero everything again. And zero the force. And then you start your incremental application of torque. All right, so any questions on the experiment? Again, this is the same setup that we have in our lab, and it's the same setup you all actually use for shear force in a beam, right? The only difference is we take the beam off and we put in this new setup right here for torsion. So that's the same thing that we were gonna do for you guys if you were in the lab. So any questions?
Yeah, so the machine's the same machine, so we'll just refer to it by the same name as in our other one.
Yeah, I believe I can't see the name right now, but I believe it's the same manufacturer. Yes, and it's the same equipment that we have. Correct. Yep.
So when you do the incremental force, the torque, is that just the force times the length of the rod that you're doing?
No, not the length of the rod, right? So the torque, basically, if you think about a wrench, right, and you're trying to turn a nut on your tire, right? It's that force that you put in on there, but you're going to multiply that by wherever your hand is on the wrench all the way back to the nut, right? So there's a distance on this setup right here, not on the rod, but from where you're applying that force back to the center. So it's a small distance, and that distance is 0.05. So let me see the data that I'm going to send you guys. I'm trying to see if I can find it here. You are doing torsion. So experiment 1. And I don't actually have it shown here, but the distance is 0.05 meters, that torque arm length, if you would. So therefore, if you have a force of 1 and you multiply that by 0.05, that one force is 0.05. If it's 2, you multiply that by 0.05, you're going to end up with a torque of 0.1. So yes, so you just multiply by 0.05. I'm trying to see if I have it in here anywhere. I don't. I just have it in my cell. But the torque arm length that you're mentioning is just 0.05. Does that make sense?
Yep.
Cool. All right, that's 0.05 meters. All right, so quickly, I'm gonna go over the test that you were supposed to do. So there's, in essence, 3 parts, right? Part 1 has 2 parts, right? So the first part for the first experiment, which is torsional deflection of a solid rod. So in essence, we're looking at just the torsional deflection of a solid rod. Part 2 would be torsional deflection of a solid rod, but we're now looking at a comparison of 2 different types of material, right? Steel and brass. The third was looking at an effective rod length. So this really is all the first experiment, 1 and 2. This is your second experiment, effective rod length, basically changing the rod length and looking at torsional deflection. But for your lab, you were only going to use 1 torque, right? So, or 1 force. Instead of incrementing the force for this second experiment, you're just going to use 1 force or 1 torque and just change your length. So you're going to look at what 1 application of torque does on, or what the changes of length actually does on angular deflection, just 1 torque, right? And then the last one was to compare solid rod and a tube rod. All right. So for the first part, right? Again, same thing. You read every angle of deflection or angle of twist. For every 1 Newton of force, up to that 5 Newtons that we talked about, right? And of course, here it is, right? So you take your force and multiply it by this torque arm length of 0.05. And therefore you get your torque. Now you're going to have data set for steel. You're going to do it again for the data set for brass. And so what I'm expecting to see is a graph plot of torque versus angle for both. Excuse me, I'm trying to hold it in and it won't let me. But you're gonna plot a graph of torque versus angle. And the angle is read in degrees. So you're gonna have, for that first experiment anyway, the angle is in degrees. So you can simply plot your torque and your angle of degrees for steel. And for brass, you're gonna plot your torque and your angle of twist. You can do it in degrees or you can change it to radians if you want, but I'm expecting to see plots like this, right? Torque versus angle of twist. I get mine in degrees. So this is kind of what I expect to see from your data. So going back, discussions. These are the types of discussions I would expect. Look at your data, right? Tell me about your data. What is your data telling you? Increasing? Why is one lower than the other? And then I need you to talk about 3 applications where torsion deflection is not desirable, and talk about just 1 application where it is desirable. Right? And here is just a prediction, right, on your opinion of what you think the behavior is going to do. Right? What happens to relative stiffness? We talked about relative stiffness in the equation or relationship is given above in a previous slide. Right? So what would happen to relative stiffness if the diameter of that rod increases? Right? So I need you all to give me some discussion on that. For part 2 of that first experiment, we need to know the diameter. Hopefully, well, not hopefully because y'all are not in the lab. So I was going to say hopefully y'all didn't measure the diameter, but y'all going to be given the diameter in this case. And given the diameter right, y'all can calculate polar moment of inertia, right? We just did that on one of those questions, FE exam questions for the Mental Engineering exam. All right, so y'all can calculate polar moment of inertia. So in essence, then the results we expected from that is I want you all to calculate angular deflection, P, TL over JG, right? And then you're going to look at torque times the length. Then you're going to look at J times phi. That should be phi. I thought I changed that. It's not theta. Save. Right. Yeah, y'all are going to look at J times phi. Right. And so therefore, of course, if you were in the lab, you're going to fill out this table. And then you need to plot TL against J times phi. Right. And if you plot TL J times phi, of course, you're going to have a graph. And then I want you also to plot stress versus strain. You can calculate stress, torsional stress. You can calculate shear strain, right? So you all should be able to plot stress versus strain, right? And if you know you're looking at that torsional stress, torsional strain, and then you're looking at TL versus J times phi, I want you all to be able to interpret that graph of TL versus J times phi, right? What does the gradient represent and what is its value? I'm gonna go back to the equation. Now keep this in mind, right? TL J times phi. All right, so let me go back to this equation. Phi equals TL over JG. So if I ask you to plot TL and versus J in phi, what is the slope of that graph?
Is it the inverse of G?
Well, depends on which axis you put TL on, right? But in this case, if I put G at the top, if I try to equate what G is from this equation, G would be equal to TL over J times phi, right? So if TL is on your y-axis and J times phi is on your x-axis, the slope of that graph should be, in fact, your shear modulus of rigidity, right? And we know how to calculate shear stress. Well, we know how to calculate shear strain, right? And we know how to calculate shear stress or torsional stress. And you can look at torsional stress, torsional and torsional strain, and you should be able to get G as well from that graph. So let me go back to that. Right. So now interpretation of the graph of stress and strain, right? You're going to have G as the slope of that graph. And so what I want you to do is make a comparison of that G value that you get from the shear stress, shear strain, or torsional stress, torsional strain graph, I should say, right? And from what you determine from the TL versus J times phi graph, right? Are they equivalent? Are they not? What if they're not? What could we change to make them more equal? Right? So those are the types of discussion I expect from the first experiment. From the second experiment, we're going to look at the brass rod, right? So you're going to use the brass rod to do the effect of rod length on torsion deflection. Hopefully we have the diameter of the brass rod, or you're going to have the diameter. I'm going to give it to you. And you're going to also be able to have the angle of deflection, right? That's part of the experiment that we need to read that angle of twist every time we put a torque on the rod. But we're going to do that at different lengths, right? So for each length, 500 millimeters, 400 millimeters, 300 millimeters, 200, you're going to have a certain angle of deflection. And I want you to plot angular deflection against rod length, right? And these are the discussions, right? What is that graph telling you, right? Tell me, actually look at the graph. Maybe the trend. What does the graph mean? What is the graph saying, right? So tell me about the graph. And another concept question, right, that I want you all to discuss and talk about is this right here. Basically, it says that front-wheel drive vehicles, right, have unequal drive shafts, and because of that, the gearbox is not at the center, right? It's on one side more than the other. So you're going to have a longer shaft coming out of that gearbox, right? That might go to maybe one of the front wheels, and a shorter gearbox, a shorter shaft from that gearbox that goes to the other side, right? So you have two different shafts coming out of that gearbox, or two different shaft lengths coming out of that gearbox. So as I accelerate or apply torque, right, it says it's going to be a mismatch in length, right? And that mismatch is going to cause some kind of undesirable effect, right? Why is that? As the torque is applied or the car accelerates, and what can we do to eliminate that effect? So another concept questions. Basically, this actually happens in some of your cars, especially your front-wheel drive vehicles, I believe. I could be wrong. Maybe the mechanical engineers can tell me different. I'm sure they know why. All right, so that's the second experiment. And in the third experiment, we're going to compare the solid rod and a tube, right? So what we're going to do, we're going to use the brass. And remember from the first experiment where we had a certain length and we just applied the incremental torque, 1 Newton, incremental force, 1 Newton, 2 Newton, 3 Newton, 4 Newton, and 5 Newtons. We're going to do the same thing on the tube brass. And then we're going to try to compare the two, right? So you're going to apply 1 Newton up to 5 for the tube. You're going to convert that force to torque. And now you have your data set course, with your angle of twist for every one of those incremental torque. And then you can now calculate, compare the two, right? So of course, calculate J for the solid rod in the tube. And this gives you a density of your brass rod, right? And this is applicable for both the solid and the tube. It's a nominal mass per unit length, right, of rod. So 8,450 kilogram per meter cube for brass, right? So again, maybe you might be able to use that in some of your discussions or just some of your analysis. Comparison of the J values, and you're going to actually notice that there is a difference in the J values, which of course it's obvious, right? Because one is solid, and they get the same outer diameter, hopefully, and one solid and the other one's hollow. So for the hollow rod, you're subtracting that inner part, the J for that inner part. So you're going to have different J values. But I want you all to comment on the efficiency of designing torsion members out of a tube instead of solid material. Now, this might take some of you back, but if you all remember some couple of years ago, maybe 3 years now, I can remember exactly, but Ford made a big deal and put out a commercial about their, not the drive shaft, but their chassis, right? And how very good their body or that chassis was because of the type of metal and because it was a hollow metal. They made a big deal about all this thing, right? But why is it better to have hollow steel or brass in this case than a solid steel if you're worried about torsion in that member, right? So I want you to think about that and at least give me some kind of discussion on efficiency. All right, and of course, some kind of recommendation at the end of the report. All right, so that's my expectation. I'm sorry about the lateness. That's not a word, is it? Sorry, I was late.
It'll work.
But again, I think in another week when you'll really start to get into this, you're probably going to forget some of what I said. But the slide should be on Moodle, so you can reference the slide. Make sure you watch that video again because it's helpful. And again, if you have questions, even before we meet next week, just send me an email and I'll try to answer. All right. So any other questions before we sign off?
I know you said that we have.
Again, I'm considering trying to post this Excel sheet. As you can see, I have all 3 experiments, so that's the data that you're going to get. But I started doing an analysis on the first experiment. And so I might actually maybe post this, maybe, but I'll think about it. All right, so any other questions for me?
Nope, I'm good.